So for a while now, we've been using the disks method of calculating volume. We target some area, some region, and we would rotate that region about some line, and that would give us some 3D volume. And what we wanted to do, the whole sort of foundation of the disks method, was to envision this volume as just a bunch of thin disks stacked onto each other. And once we were able to imagine those disks, we executed this series of steps, the disk approach for calculating volumes of rotation. Now, this is Shell's method for calculating 3D volumes. A shell is one of these things. It's basically a perfectly cylindrical donut. It's a cylinder, but with this big hole, this big cavity in the middle of it. So, instead of envisioning our target shape as a bunch of disks put on each other, we need to start visualizing it as a bunch of these shells. That is what we're aiming for. So, just like we built up a series of steps for building each disk, and then at the end adding them all up to get the total volume, we're going to build a new series of steps to build each one of these shells. And then at the end, we're going to add up each one of our shell volumes to get our total volume. That's where we're going here. Okay, so let's build up our shells approach by looking at a specific problem. Same class of problem, just want to rotate a region bounded by some curves about some axis. Let's sketch this curve. So here is 2x squared minus x cubed. A couple of points of interest here. We have a double root here. We touch down on that x-axis and pop back up. Here's a x-intercept here. X is 2, y is 0. We also have a local maximum right about at x is equal to 4/3. I won't show the process of graphing this by hand. My advice is locate all your points of interest, your local maxes, local mins, y-intercepts, x-intercepts. That'll really help you graph these curves if you have to graph them by hand. But I won't show that now, just so we can fast forward to where the shells come in. Of course, I have y is equal to 0, the set of all points that have y coordinates of 0. Now this basically means that we only care about positive x's. So right off the bat here, I'm going to ignore basically this whole left side of our graph. Alright, so here is the region enclosed by these curves. And apparently I want to take that region and rotate it about the y-axis to form a 3D shape. And here's the shape I'm going to get. And here's a 3D look at that shape. So we want to envision this 3D shape not as a bunch of disks together, but a bunch of shells together. And that's a bit tough to do. So here's how I'm going to explain it. So for our main graph, imagine taking a rectangle. And imagine taking that rectangle and revolving it, rotating it about that y-axis. That will get you one of those shells. So here is that rectangle that we swooped around our y-axis to make one of our cylindrical shells. Here's another one. I can imagine a smaller rectangle right here, and I can imagine revolving that guy around our y-axis to make another one of those shells. So here is that rectangle, that little rectangle that we revolved around the y-axis to make that little blue shell. And of course you can keep on imagining us doing this process for all these little rectangles. So hopefully this allows you to visualize our 3D volume as a bunch of shells. And similar to how we built the disk method, we're going to go through the steps, write up the math for calculating the volume of one of our very thin cylindrical shells. And then at the end, we're going to add up, using the integral, all of these thin cylindrical shell volumes to get our total volume of the target shape. So, our first step is that we want to form the small rectangle that we want to rotate around the axis. So, here's a small differential rectangle. Differential just means very small. So let's form it. Let's write the math for its area. Well, area of a rectangle is just length times width. This length is just the y-coordinate of this point right here. Okay, easy enough. Y. Now what is the width? Well, the width is a tiny bit of distance in the x direction. That's going to be dx. So y times dx. Now, I have to transform this y to be in terms of x, because you know that if I have an integral, which is what we're building up to, of course I wouldn't be able to perform this integral because I have a y there. I can only perform my integral here if what's inside matches my differential here. So it's true that I want the y coordinates of this point here, but let me just write the equation in terms of x that gives me those y's. So what this equation gives me at this moment is that when I plug in the x of some point, plug that x into that equation, gives me the y, and take that y, that length, and multiply it by a little bit of dx. There we go. There is the area of that small rectangle. I can plug in a bigger x over here. Maybe that would be 1.75. Plug in 1.75 into the equation, gives me the y. Take that y, multiply it by dx, gives me the area of this tiny rectangle. Alright, looks like I formed the equation that gives me the small rectangle. And what we want to do with this small rectangle is revolve each one about our y-axis to give the shell. That will be our next step. So let me just use this smaller rectangle so I can not run out of room. So I want to take this rectangle and sweep it across that y-axis so that I can create my thin cylindrical shell. Now, how am I supposed to calculate the volume of this cylindrical shell here? Well, imagine taking that shell and cutting it with some scissors and then unraveling it to make sort of a straight block. You would get this. And if that's kind of hard to see, that's fine. Imagine that you had some yarn, a circle of yarn, a circle of string. You can imagine that if you took some scissors and cut right here, you could take these ends right here and stretch them out to form just one line of string. That's basically what we're doing here. So how are we supposed to calculate the volume? Because this guy right here is really, he's the cylindrical shell. We haven't changed his volume. We just took our guy here, cut it with some scissors, unraveled it to get this. So these two guys are really the exact same volumes. We're just looking at this one because it's easier to see how to calculate its volume. Here we go. Remember, go back to our previous videos. One way of thinking about volume is the area of the base times some height. Well, we already have this area right here. Remember, that area is just our dx times our y coordinate here. We have that. That's what our equation is telling us right now. All we need to do now is multiply this area by this height, this length right there. Well, how on earth are we supposed to figure out that length? Well, go back to our string example. In the beginning, I just have this yarn, and I don't know its total length here. I don't know this length, but I do know that this yarn can form a circle of radius r. Well, what's the circumference of a circle? Well, the circumference of the circle, of any circle, is just this length right here, 2 pi r. Well, that's the same thing as this, 2 pi r. And it's also the same thing as this length right here, the length that we're actually trying to get, 2 pi r. R is just the radius that we swept, that little area around our axis. Over in our bottom left, it is this distance here. That's our r. And over on our main graph, here it is. Again, this is the r, the radius that we're using to sweep that tiny rectangle around our y-axis. So, let me erase our yarn example here, just to make room. I'm going to put it in the right over there. So going back to our math, what I need to do is multiply this unit that is giving me the area of our little rectangle, this guy right here. I have to take that area and multiply it by 2 pi r. That's what we're looking at right here. And what is r? Well, looking at our main graph, r is simply the x-coordinate of that point. So instead of r, I can say 2 pi x. And now we finally assembled some math that gives me the volume of one of our cylindrical shells. Now that's a lot to digest, so let's go through another little rectangle situation real quick. So we start by crafting one of these small rectangles, the area of one of these small rectangles. And of course, the area of any rectangle is length, right here. That's the y-coordinate of this point. That's this guy, times the width, which is going to be a little bit of distance in the x direction. That's dx. Because this is dx, of course, I can't simply write y here. I have to write that y in terms of x. Plug in an x, and it gives me the y. So they kind of mean the same thing. But of course I need x to be with this dx, so I can add up all these little cylindrical shells at the end. So now I have the area of one of my little rectangles. And now we want to sweep this area around my y-axis to make one of my thin shells. Oof, that's a bad one. And what we've reasoned that we have to do is that we have to take this area and multiply it by this height here, which is 2 pi r. 2 pi, nice. Well, R, I can envision R. I can envision the R that I'm using to sweep that orange volume. And it looks like in all of the cases, the R is simply the x-coordinate of that small rectangle. So here we are, 2 pi x. So now when I plug in an x to this whole equation, I get the volume of one of these shells. So let me just change my step here. I wanted to say form the area of the small rectangle that you want to revolve around the axis. So let me just change that real quick. So then we had that step 2. So we took this area here and we multiplied it by 2 pi r, where r is the radius that we were using to sweep that small rectangle about our y-axis. And we saw that in every case, all that r was the x position, the x-coordinate of that rectangle. So now my equation gives me the volume of one of those really thin cylindrical shells. And finally, now that our equation, we plug in an x, and we get the thin cylindrical shell at that x, we get that small volume of that shell. Of course, we want to just add up all of these shells, all of these small volumes. Well, where do we want to start? Well, my first shell is going to be tiny. It's going to be basically right here. And this is a dx integral. So, what is the x-coordinate at this point? This is x equals 0. Now my last shell is going to be basically this guy over here. It's going to be a very, very flat, but a very, very wide shell. And the x-coordinate of this guy will be x equals 2. So, we have finished the integral. And now, of course, we just have to do the math now. And if you carry out that math, it will get you 16 pi over 5. So, that is the cylindrical shells method of calculating volumes. It's going to be these 3 steps right here. And in my opinion, it is the hardest volume calculation method because it is quite hard to envision those shells and take those areas and rotate them about and find the R. It gets pretty tricky. So just really focus on understanding these steps here. And in my opinion, this whole 2 pi r thing, that's just crazy. So definitely take your time and try to understand this concept from this level. So there's just one more thing I want to say. Most of the problems that ask us to, form a 3D volume and calculate that volume, most of these problems you can calculate either using disk method or shells method. You can use either or method to calculate the volume of that shape. And of course, both methods will give you the same answer because, it's the same volume. But there are certain problems where disk method is better, easier, and there are certain problems where shells method is better. The problem that we're looking at actually is one of them. Imagine that we wanted to do the same problem but with the disks approach. Take this area and rotate it about that y-axis. This would be a washer problem because I can't, strictly visualize that 3D volume in the bottom left there. There's a bunch of pure disks. I can visualize them as washers though, which means I need to do the big volume minus small volume approach. I could kind of split my curve into 2. This segment here, if I rotated it around, that segment would basically give me the small volume, and I'll keep this segment right here as green. This segment here, if I rotated that around the y-axis, that would give me this entire volume, the big volume, and then I could do the subtraction. Let's look at the small volume real quick. If I wanted to do the disk method to calculate that yellow volume, here's the radius of each one of my disks. See that radius? Alright. Each one of those radii are going to be x's, the x coordinates of those points along that yellow line. Which means I need this equation flip-flopped. I need x by itself. The problem is that it is impossible, at least on paper, without assistance of like a computer or something, it is impossible to get x by itself. That cube, that square is making it really, really hard. So since we can't get x by itself, and I need those x's, because those are going to be the radii of my disks for the smaller volume, and since I can't get x by itself, I can't carry on with the disk method. Shell's method is really the only way to do this problem. So, most problems, you can use both methods. Shells will work, disks will work. But for some problems, shells will work and disks won't. And of course, for some problems, disks will work but shells won't. So just in case you're running into a wall in one of your problems, just try switching your method. Alright, long video, but hopefully this shells approach makes sense. It's definitely the hardest of the volume calculation methods. In the next video, we're going to do a whole bunch of shell problems rotating about, we rotated about the y in this case, but in this video we'll do it about the x, we'll do it about any horizontal line, any vertical line, just so we can really, really nail down and visualize our shell method.